Today we're going to be taking a look at graphing radical functions, but I'm going to show you kind of a different way to think about it, where we're not exclusively just using transformations, we're not exclusively just using t-charts, but we're trying to combine the best of both worlds to figure out how it is that we can go through and create one of these graphs in a way that makes sense. So first off, we need to point out that what is a radical function? Well, a radical function for today is just going to be describing what we call the square root function. So we're going to be graphing f of x equals the square root of x. This is ultimately going to be what we call our parent graph. It's kind of the source that all of the different transformations can be applied to. But we're just going to take a look real quick at how we can go through and sketch a graph of the parent radical function f of x equals the square root of x. Now, the way that I like to teach this is I like to use a SMART chart, okay? We all know that it's possible for us to graph any function by just creating a generic t-chart. You probably started doing that when you first learned about graphing. You would go and you'd make a t-chart, and in that t-chart you'd put -2, -1, 0, 1, and 2. Plug it into the function, connect some points, make a pretty picture, and give yourself a high five. Well, as we get more and more involved in different types of equations within algebra, we start noticing that maybe that doesn't really work out so great, right? Because, I mean, what if I was to say start off with this very generic -2, -1, 0, 1, 2 thing, and I'm trying to go through and graph a square root function? Well, I would first be going and trying to evaluate the square root of -2. Well, wait a minute, that's I root 2. Can you graph I root 2 on the coordinate grid? Nah, this is the real number plane, okay? That's imaginary, so you're sad. Then maybe you try and plug in -1. You say, okay, well, maybe this one will work out. So the square root of -1, and then you realize that's just I, which is another imaginary number that you can't graph. So again, you're sad. So you're 0 for 2, and maybe you're thinking, is this the best way to do it? I don't know. So let's just try and keep going, right? So we do square root of 0, and haha, finally, a number that we can take the square root of. It's just 0. So I can go and plot an ordered pair where when the input x is 0, the output y, or f of x, is 0. So that's just this point on the origin right here. Then I go and I plug in 1, and I say, all right, I'm going to take the square root of 1, and the square root of 1 is 1. Wow, both of these are making me really happy, okay? Happy numbers. So I can also plot the point 1, 1. So I go over my little graphy graph over here, and I plot 1, 1. Then I do the square root of 2, okay? Because I'm doing the square root of x, right? And I plug in that 2, and all of a sudden, now I got to go get a calculator. If the square root of 2 is 1.41421356. I don't want to graph all of that. Maybe I just go and say it's approximately, okay, like 1.41. Like, I can graph it, but is it easy to graph? Meh. So that's kind of a math point. So just going through and picking kind of your generic 5, we got a sad face, happy face, meh. Okay, because 2 and 1.41. All right, I guess I could probably guess it's right there. But you can see this doesn't really give us a lot of points that we can make a good-looking graph from. So this is when we need to start thinking mathematically, and don't just use a generic t-chart, use a SMART t-chart. What kind of function are we dealing with? A radical function. In a radical function, I'm taking the square root of things. Well, why don't I intentionally try and pick numbers that I know the square root of already? Numbers like 4 and 9, also 1, 0. What else? You go like 16, 25, 36, 49, okay? Pick the numbers that you know will work before you even go and plug them in. It's brilliant, okay? So we're going to use a SMART t-chart to go and do this. So if I skip 3, because I know I don't know without a calculator what the square root of 3 is, but I plug in 4, that'll give me something I can actually graph. So I plug in 4, the square root of 4 is 2. That's a whole number. It makes me happy. 1, 2, 3, 4, 1, 2. All right, and then if I go and plug in 9, well, the square root of 9 is the whole number 3. Wow, that's such a pretty number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then up 1, 2, 3. And I have this whole series of points that I can use to go and graph, terribly, but close enough, what the square root function is going to look like. And hopefully you all remember from your time back in Algebra 1 in 8th grade that the square root function pretty much looks like a little swooshy looking guy. Okay, I realize this isn't very swooshy, but you get the idea. All right, so what have we talked about thus far? Well, when we're graphing a radical function, we want to try and use a smart t-chart to do it. We don't arbitrarily and randomly just pick numbers to plug in. We know that we can't take the square root of a negative, so don't plug in numbers that make what's under the radical negative. We also know that there's a finite list of perfect square numbers, so let's pick those ones, okay? Let's pick the square root of 0, the square root of 1, the square root of 4, the square root of 9. Those are your smart numbers to choose. All right, so this is a real basic, real simple one, okay? What happens if we start going through and adding all of these different transformations? Well, we can still go through and use our smart t-charts with transformations, right? So if we look at the parent graph being f of x equals the square root of x, the transformative function for that parent function would be g of x equals a times the square root of x minus h plus k, where each one of those values is going to have some sort of transformation to the parent graph, okay? I kind of want to show you guys what it looks like. It's kind of helpful in knowing really what the graph should look like before you even start graphing it. So first off, we have this numerical value of a. It's important to note that a can be positive or negative, all right? And it can also be 1. If a is 1, we don't really see it written there, so it's not really doing anything to transform the function, okay? But the value of a is going to do one of two things, okay? It can stretch or shrink the graph. It can also reflect, okay? The value of it is going to be the stretch or shrink, okay? The sign of it is going to tell you whether it has been reflected over the x-axis or not. All right, what else we got in here that's a transformation? Well, we've got this minus h. This minus h represents a horizontal shift, okay? So that's going to go and shift the function to the left and to the right. But it's important to notice, okay? This minus sign is included in the transformative form. So it essentially means that h actually does the opposite of what the sign does. So if you see a minus, say the number 5, well, that's going to shift it 5 units, but not to the left. It's going to shift it 5 units to the right. If this was like x plus 5, well, it's going to shift it 5 units horizontally, but it's going to go actually to the left, okay? So it's the opposite of what the sign is the direction of the shift. Then we get over here to k, our last one, okay? And k here is our vertical shift. So that's going to move the function up or down. The good thing about k is k doesn't tell a lie. If it says plus a certain number, you move the graph up a certain number. If it says minus a certain number, you move the graph down a certain number, okay? And if you think about it, it really makes sense because you're kind of going through and doing all the algebra and most of the arithmetic first, and then you're either going to add a number to it or subtract a number from it, which really means that you're going to add a number to the output or subtract a number from the output. The output is the y value, so you're increasing the y or decreasing the y, so that's why it's a vertical shift there, all right? So as an example of how we can use some smart t-charts with our transformations, we're going to go and take a look at the following example, okay? So we're going to say that the function h of x equals negative 3 times the square root of x minus 2 plus 4. All right, now, before I even get started graphing on that, there's just one little thing that I want to go through and show you. I'm going to take my best guess as to what the transformations look like. So my parent function is the function f of x equals the square root of x. And I know from my previous example that that's going to look an awful lot like this. So 1, 2, 3, 4, 1, 2, and then 9, 1, 2, 3. So I know the parent graph is going to look something like this. Okay, what are these transformations going to do? Well, negative 3 tells me that it's going to be reflected over the x-axis, and because this value is 3 is greater than 1, it tells me it's going to be a stretch. So it's going to get like pulled towards the bottom. Okay, it also tells me that the graph has been shifted 2 units to the right and 4 units up. Okay, so 2 units to the right, opposite sign, but then 4 units up, the right sign. Okay, so if we go and think about what is the most important point in the original function, it's what we call the critical point, and it's actually where the function starts. This function starts at the origin, 0, 0. This function, its critical point is going to be at 2, 4. Okay, positive 2, comma, positive 4. So on the axis, I'm going to go and take my best guess and say I'll do my best guess in light blue here. So we'll go 2 units to the right and 1, 2, 3, 4 units up. So this is my guess. And then it's going to get pulled 3 units down. So, and it's going to kind of open down. So I'm going to guess that it's probably going to look something like that. Okay, that's just my guess. Now it's up to me to actually go through and verify that that is what it should look like. All right, so let's think about what our smart numbers are when we're dealing with radicals. The smart numbers are the numbers that you can take the square root of. Numbers like 0, numbers like 1, numbers like 4, numbers like 9. You could go 16, but do you think we can fit 16 anywhere on here if it would work out? Probably not. So we'll just kind of stick with these ones. So what we're trying to do is we're trying to get what is inside of the radical to equal these smart numbers. So literally set them equal to what is inside the radical. Because if what's inside the radical is equal to 0, I can take the square root. If what is inside the radical is equal to 1, I can take the square root. If what is inside the radical is equal to 4, I can take the square root. So let's just go ahead and use that, okay? So that's going to give us a list of 4 smart numbers to go and use for this particular problem. So if 0 equals x minus 2, I'd add 2 to each side, and I would get 2. If 1 was equal to x minus 2, I would add 2 to each side and get 3. If 4 was set equal to x minus 2, I would add 2 and get 6. And then finally, if 9 was equal to x minus 2, I would add 2 and get 11. Okay? So these are the numbers that I can plug into the function that will actually give me numbers that I can take the square root of. All right? So let's go through and do a little bit of arithmetic here. So we're going to evaluate the function h at 2, then again at 3, then again at 6, then again at 11. So if I substitute a 2 in for x, that's going to be negative 3 times the square root of 2 minus 2 plus 4. Well, order of operation says do what's inside the parentheses first. There's really an imaginary, or not imaginary, an invisible set of parentheses that's kind of inside the radical. So I need to do that first. 2 minus 2 is 0. The square root of 0 is 0. Negative 3 times 0 is, you guessed it, 0, and 0 plus 4 is 4. So my first point is my critical point, 2, 4. And that is exactly where I had guessed that it was going to be. Okay? So maybe I'll even go up here and say 2, 4 is my critical point. okay? So then if I go and plug in 1, I've got -3. I'm going to multiply that by the square root of 3 minus 2, and I'm going to add 4 to that. And again, doing just a little bit of arithmetic, we're going to say 3 minus 2 is 1. The square root of 1 is 1. And -3 times 1 is -3. -3 plus 4 is +1. Okay? So if I plug in a value of 3, I get an output value of 1. So I'm going to go 1, 2, 3, and then up 1. And that's pretty close to where I guessed. Okay? I must be good at that. Next, I'm going to find the third point. So I'm going to substitute the number 6 into the function. So we've got -3 times the square root of 6 minus 2 plus 4. So 6 minus 2 is 4. The square root of 4 is 2. -3 times 2 is -6. And -6 plus 4 is -2. So my third ordered pair that I can plot is 6, -2. So I can go 1, 2, 3, 4, 5, 6, down 1, down 2. And again, I'm pretty close to where I guessed. All right. So last point that I'm going to be able to fit on the graph, I suspect, is this one right here. So let's substitute an 11. So -3 times the square root of 11 minus 2 plus 4. Do some arithmetic. And keep in mind, you can do this in your calculator, but it's almost faster to do it in your head, especially since you know you're going to end up with nice, pretty whole numbers. 11 minus 2 is 9. The square root of 9 is 3. -3 times 3 is -9. -9 plus 4 is -5. Okay, so we're going to go where x is 11, which is just off the graph, and then we're going to go down 1, 2, 3, 4, 5. So probably right about there. So you see the line where I drew the guess, how it was pretty close. Okay, now I'm just going to go through and do my best to actually kind of make it look a little bit cleaner. But this blue line here would represent the transformations that we've done graphing h of x equals -3 times the square root of x minus 2 plus 4. All right. The last thing that I want to go back and talk about for each one of these, though, is one additional characteristic, and that is the domain and range of each of these functions. Okay, so please keep in mind that the domain is the list of all of the x values that are real within the function. Okay, it's all of the possible input values. So if we go back and look at our first one, is -2 a part of the domain? Not really, because it gives an imaginary output. Is -1 a part of the domain? No, because it gives an imaginary output. But is 0? Yes. Okay, so the domain here actually starts at the value of 0. Okay, and it includes 0. We actually can have 0 there. All right, but then you'll notice all the numbers that come after 0, 1, 2, in this case 4 and 9, those are all real numbers, and they're all going up. We go from 0 to 1, 1 to 1.4, then to 2, then to 3. We could keep going, and we're going to keep going until we get all the way to infinity. So the domain of this function is written in interval notation from 0 to infinity, because all the possible x values start right here, and they'll keep going all the way to the right. Okay, the range is similar, but it's all about the output values. So if we look at the output values, the first output value I see is 0. When I look at the graph, I see that no part of the graph passes below the y-axis where it's 0. So the range is also starting here at 0. But as we look, each one of these values is above the one that came before it. And even though it's not going up really quickly, it is going up. So the range is everything from your critical point all the way up to where y is infinity. So the range here is going to be also from 0 to infinity. Taking a look at the second one that we went through and did, can we figure out the domain and range of this one? Probably. Okay, so domain and range. So let's do this one a little bit more graphically. Okay, the t-chart is really just telling us exactly where those points are, but I can also look at the graph and see. So the domain is all the possible x values. My critical point here was at 2, 4. I don't see any x values that are actually to the left of or more negative than 2. That's kind of the starting point on the x-axis. Okay, so the domain starts at 2, and it keeps going to 3, to 6, to 11. It could keep going all the way to infinity. Okay. The range, on the other hand, though, remember, we always go and list these from smallest to largest. Because this is going down, it looks to me like it's going down towards where the y value is eventually going to hit negative infinity. So negative infinity is actually the smallest value that you could have in this function. So we would write that first, because it's always least to greatest. I will continue to have real output values all the way until I get to, well, this point right here, which, look at your critical point. That's where y is 4, okay? There's no points on this graph where the output is greater than 4. And because that's a dot point, we're going to go ahead and use a hard bracket for it, okay? So domain and range are hopefully a review for you guys. Remember, just a list of all the possible x values and all the possible y values, but we always go and list it from smallest to largest. All right. So please make sure that if you guys have any questions over this stuff, that you go and ask it, especially as you're trying to work your way through these problems on your own. I also want to encourage you guys to use your graphing calculators to check what you're doing by hand. Yes, it's important that you understand how to do it by hand, because sometimes you mistype something in your calculator and you need to recognize, hey, shouldn't it look different than what the calculator is telling me? Sometimes your calculator runs out of batteries or you forget to charge it. So that's another case where maybe doing it by hand and knowing how to do it by hand is going to be a valuable mathematical skill.